Oh, okay, recording has started. Also, my research team and Jorge's team also have done some experiments using the ACC. And as well as Dr. Xiaopeng Li from University of South Florida. He has done some ACC tests as well. So these experiments provide a good amount of data for the public to understand the features of ACC and also to promote the future research. So that's why we have this ACC initiative with the aim to better disseminate the research outcomes and also to facilitate further research and applications in this area. So this initiative has two items. The first one is this ACC Webinar Series, and the second one is a designated web page for the ACC resources. I will provide a little bit more details of each. So regarding the ACC Webinar Series, the topic will cover basically anything relevant to ACC, such as the ACC field experiments, analysis, modeling, simulation, control, etc. We are very happy that right now we have already we have some speakers confirmed, including Christine, also Dr. Makridis, Vincenzo Punzo, Dr. Yang Zhou from UW Medicine, and also my student Tinan Li, and also Jorge's student Hao Zhou will present. The detailed schedules of the ACC webinars can be will be updated on the website. And here is a snapshot of what we have right now. So more speakers are welcome. So if you would like to share your research, please feel free to let me know. And we are very excited to learn more about the progress in this area. So that's for the ACC webinar series. Second item, so along with the webinar series, we are also launching an ACC website. Here is a snapshot of that. The aim is to make this a repository of the ACC resources for the public. The content it will have, I say will because it's still under construction. So it will have different components there, including the experiment data to share with the public, the research outcomes, webinar info, teaching material, and probably other things. So if you have or you know of any relevant data or material that you would like to share with the public, please let me know. And by the way, just one last note. So we are launching this initiative on behalf of as an activity of the ACP 50, the CAV subcommittee, and well, everyone is welcome to join the subcommittee because this one, yeah, basically, you as long as you're interested, you can email the chair, which is Stan Mahenda, and then you can become a member of it. So that's for the subcommittee. After this very brief intro of this ACC initiative, so today we are very happy to start the first webinar, which will be given by Dr. Christine Buisson. So Christine is going to introduce her work on the reaction times in ACC car following experiments, a comparison between the datasets and the determination methods. I'm going to do a very brief intro of Christine, although I think most people in the audience here know Christine very well because she has been working in the traffic flow theory area for several decades. So she's a good old friend. Okay, so Christine is a researcher and teacher in traffic flow modeling, observation, and control for about 30 years. She is devoting her research to the link between observations and models, with a particular focus on the model's limits exploration. Last 2 years, to try to gather open sources data about ACC experiments to make cross comparisons and contribute to a query evaluation of the impacts of this ACC on the human-driven traffic. So this is a very brief intro. Christine actually has a lot of achievement, but I guess she wants to save the time for the technical research talk. So I guess we can jump to that part directly. Christine, did I miss anything?
No. Okay.
Okay, then let me share.
The achievement I'm most proud of is to have been the first nominated people for the Best Reviewer Award of the Traffic Flow Theory Committee and Characteristics. That's my best achievement in my career until now. Okay, hello everyone, thank you for coming. It's really nice to see so many people a few days before TRB deadline. I'm happy to share the results we obtained with my two students, Jan Metelski, who is a master student, and Carlos Gomez Patino, who is a PhD student. Both worked hard to make the results you will see today, and I want to thank them and also to apologize for some limitation of the results, but you know, this is a webinar and we are planning to make a paper sooner or later. It's okay with the screen? You see it perfectly, no problem? Okay?
Yes, very good.
Yes, we're fine, Christine.
Okay, thank you. But first I want to make a bit detour before we start. It's ACC research that will be presented during this webinar series is possible thanks to the sharing of many efficient teams' efforts, and that's very nice. And I like the idea of sharing, and Jorge remember maybe that during his MFD data collection effort, I provide some almost 10 years ago. So it's a continuation for the community, but for the moment, to my opinion, this is too much limited to open data on open source. And I want to remind you that the true pillar of open science are 6, and we have not to forget all the 6. In particular, I think that regarding the question of ACC, the pillar of knowledge sharing is important, because we have to spread what we know in for public authorities and for citizens, and we also can benefit each other from better research methods, like the one provided by reproducible research. And also there is the question of open access and research assessment, which is behind all this stuff. So I think as a committee, we may think further to this question of open science, and the ACC initiative is a very good path in this direction. Thank you, Andrew, Jorge, and colleagues. So let's go to the introduction itself. Why should we make ACC Webinar Series? As I am the first one, I permit myself to go a bit back to basics. So all of you know that capacity is the inverse of the reaction time. So ACC, if they keep their promises that they were having at the beginning of the history of ACC, they should have been a reaction time of 0.5 seconds, which would have directed to a very high capacity, but we will see that we are more in this region now from what we have seen. This has, of course, an impact on capacity and safety, and we have to go to a better understanding on that. And to better understand, many authors contributed on ACC reaction time determination. I will take the slides of Professor Peng Li, who is in the audience. Thank you for coming. And I think that the methodology, the experimental method, is very similar in many of the ACC databases that Denju just talked about now. And all the system is very similar now. GNSS positions are precisely recorded, and there is a set of speed plateau with a recording of the impact of the variation of the leader speed on the follower speed. Please note that US DOT made an experiment earlier with less precise measurement method, and with that data we didn't obtain such precise results as the one we will present now. So in Xiaopeng Li's experiment and his colleague, we have, like you can see it, a set of plateau and the reaction of the follower vehicle. So there are many things we can study in that. The first one is the reaction time, but I think the question of oscillation is very important, and thanks to the quality of the data, we can go in this direction in further research. So many authors provided reaction times measurement methods, and they are very different one to the other. The first team in the recent works is the team of Professor Works, presented in a paper of Günther recently, where they calibrate the optimal velocity model on all the trajectory of the follower. So the complete information of the trajectory is used. Michael Makridis, who is also in the audience, thank you for coming, is using and proposing another method based on cross-correlation, and this method focuses on reaction periods. So it's really different in terms of the way you catch what is the response time of the ACC cars. She and Lee also use all the trajectory with a simple linear relationship of the acceleration, and they use their dataset. In preprint, Tianan Li, Danju, Chen, and many others who also are in the audience presented a complete analysis of the 4 datasets that are available now. And it's really interesting to know that they didn't calibrate a model or identify reaction instant to deduce reaction times, but they fit the linear relationship of which is the basis of Newell's model. So our aim is to compare various response time on various data sets, and we used only 2 data sets, but as I know, the number of the available ones will increase, and so that's a good news. So we have 4 methods. The first 2 are based on observation. We use the Makridis method, like it is presented in the paper, in IEEE paper. We use an adaptation of Tianan Li's et al. Method with a linear relationship of Newell's relationship. We use also the car following equation of Professor Li's team, and we calibrate the equation and obtain a response time, which is the optimal tau of the calibration. And we also use another method based on calibration, which is using a much more complex model, the Gibbs model. And so the four methods are really different. In the two methods at the bottom are very similar because both use calibration method, but the two on the top are based on observation, and so we have different way of measuring response time. So if we go to the curve following law, we want to calibrate. There is the equation presented in Shi and Li. So this is an equation where the acceleration is directly proportional to the distance with the leader and the speed, and the reaction time of the speed is the reaction time, excuse me, is multiplied by the speed, and there is the proportion, another factor, which try to minimize the difference in speed. So if K2 is near 0, then the model is very similar to Newell's one. And if you add a term with K3 proportional to the distance, you have the Tamper's model. And if you go to the Gibbs model, then you can see that it's much more complicated. The equation is kind of nightmare with numerical constant, which is always a surprise to me. And you can see that the role of reaction time is much more important, and it intervenes in many more occasions than previous equation. So to calibrate, we use Punzo, Zeng and Montanino's recent paper in part C, where they analyze many calibration papers and many methods and compare all of them with a very detailed methodology. So I encourage you to read this paper, as the others, right? And as they say in an earlier paper, we use a genetic algorithm to explore the space of the possible parameters. And we choose a normalized root mean square error of the combination of spacing and speed. So with the two datasets, we have an input trajectories of a set of 90. From each from there, because we selected only the first ACC vehicle trajectory. We want to see how ACC reacts to human-driven behavior. We didn't want now, but later on we see some papers showing that there is no difference in ACC behavior, whatever the position inside the platoon, but there we wanted to select only the first ACC vehicle. We consider this population as representative of the future ACC population, which is a very severe hypothesis, we know, but we have to start with something. And so we don't care about headway settings, we consider that as a population, and we want to study the distribution of the behavior of this population, whatever the settings of each vehicle. So we characterize all the vehicles of this trajectory by one parameter, which is the response time, computed according to the four methods. And but we select the part of the trajectory of a length not longer than 4 minutes to be comparable with trajectories of shorter periods. And we choose these 4 minutes to be to observe the maximal number of plateau of speeds, because we consider that we have to select periods where something happens. We reject the 16 trajectory where the normalized root mean square error was not satisfying for one of the two curve following models. We rejected also the trajectories where the Makridis cross correlation method didn't reveal a sufficient peak in the results, meaning that if you have a smooth evolution, then any reaction time can be accepted. We selected trajectories where the cross correlation was sharp enough to prove that there is something happening. And we rejected the one trajectory with a reaction time bigger than 6 seconds. And from these 64 vehicles, we had some vehicles where we had a sufficient range variation of the speed. And for these 12 vehicles, we could fit the linear relationship of Newell with a method very similar to the one presented in Li, Chen et al., but less elaborated with no wavelet or whatever method. So our 64 trajectories are coming from from 5 sources with different duration and mean speed. They come from test road and also from classic roads. And that's interesting to combine. And you can see that the classic roads trajectory have higher mean speed than the test ones. This is because apparently, if I understood well what was written, if you use an ACC in a classic road with large headway settings, then there is a very likely chance that there will be a driver who will insert inside you and your leader. So that's a problem for the measurement. So obviously, the lower the speed, the more likely the trajectory is in a test section collected. So we apply Makridis method, which is very precisely described with this set of 3 equations in the paper. And so I've said that already. So that's our results with the 4 methods. I will go a bit more into details. You can see here the 12 Newell fitting we could apply. With for those 12 red events, we trace them in the other datasets. So we can see that the first conclusion is it's different. But let's go a bit further than this simple sentence. So if we want to separate test road and classic roads, I think that yes, there is a mistake. No, there is no mistake, excuse me. So you see test roads, especially with the Xiaopeng-Li method, the test roads have higher reaction time than the classic roads. This is interesting, and you can see also that for this estimation, for example, the standard variation is not very significantly reduced by dividing the sample into 2 parts. So
I wonder whether I can ask a question now, or should I wait till the end?
Yes, please do.
So if you go 1 slide back,
yeah.
So you say speed might be the cause. I realize that there is indeed a speed difference, as you explained, between open roads and test tracks. I wonder whether you really think that the controller works differently at different speeds, or whether it's an effect of how you measure the reaction time.
I think that for Xiaopeng-Li's method, obviously there is a difference in mean speed, but for Makridis and Gibbs, you cannot say there is a difference in mean value of response time, right?
It's hard to see for me, but I just followed your words.
Yeah, but I was, excuse me, I was remembering the way we made the figure, and that's this has nothing to do with the what I said. I said a mistake.
Christine, maybe I missed something. So here the blue one is the classic. So does it mean a classic road, typical road?
Yes.
And then
test
tests are on the test track.
One is a test track and one is an open road, right? The public road.
Oh, I see. Yeah, I also have the same question with Victor. So do you think the difference is due to the road type? But I feel that maybe the sensing system has something to do with this, because on the road check, you have a much sophisticated sensing system, and then there is less abstraction or other things that your measurement probably is more reliable.
Even a third option.
You mean in test roads this is more reliable?
Yeah, I feel that probably from the test road it's more reliable. But I don't have solid proof for that.
Yes, but that's a good question.
If I may comment something, maybe these two distributions are the same. We could test that. I don't see big differences.
No, me neither, except for Xiaopeng's results, right?
Maybe not. Maybe it's good to run some goodness.
But we decided not to conduct distribution analysis on such a small data set because it makes 13.
Right, the sample size is not. Can you go one slide above? Well, here they look more different, right?
No, the red one are only the subpart of the total blue.
Oh, okay, it's not the same.
You can have the fitting of Newell.
I see.
So you have the 12 trajectory that we could fit with Newell's linear relationship, and you have the 12 values, and here you have them inside the rest. So you can see that there is no specific difference.
Right.
So that's it.
Okay. Thank you.
Having no hand to raise, I will just put myself in.
Okay.
This is very interesting stuff. And of course, I get the phone call right when I butt in.
You didn't change your ringing of phone, Ben, during all this time.
So, looking at it would be interesting to see in future work dividing this by speed. I would imagine that you're going to get different responses from the controllers at different speeds. But
I don't have the slide today. I'm sorry for that. I should have imagined that someone would ask the question. But there is no significant difference.
Well, I think probably a bigger determining factor is different manufacturers' vehicles are going to have, and possibly even different years and different models, will have different systems in them. So just as people behave differently, certain vehicles will behave differently. And then the vehicles also have, at least our car that has adaptive cruise control, has a setting for how close or how far you want to follow. And so that, presumably, the user is already setting the response time when they choose that. So
this is the headway setting, right?
Yeah. And so the headway setting is probably going to define your reaction time.
And I have the answer of your question in Tiananli and then.
Oh, I'm willing to wait till we get to it in the normal talk. I'm just tossing out some thoughts and ideas.
Yeah, but if you look at their results, we put them in yellow and green there, and they separated their analysis. So their analysis is similar to this one, and you can see clearly that there is an impact of the headway settings according to their data, right?
I can see, in addition to this, just a personal remark, as Ben brought up his personal ACC system. In our car, there's an ACC system which has two different parameters you can set. So you can set a distance and the way how quickly it responds. So well, the first one surely is some kind of headway, and the other one might be either an acceleration or a reaction time. Now, I'm still trying to figure out, but that's my personal experimentation. But it's not necessarily related to the headway.
I think, Victor, probably what you're talking about is the mode. I think we have tested one, and then it has this like power mode versus regular mode. And probably in another car brand, it has this like what's it called? Something like eco mode, and then others. So we don't know what it really means, but then we thought like it might have some impacts. But we did some testing and did not find dramatic difference in terms of the result fitting from different modes.
That's interesting. It feels different, I can say, but that's another topic for another study. So how it feels. Okay, please, Christine, sorry for interrupting. Please continue.
No problem. So if I go back to this, you can see that if you compare the results of the two calibration methods, you can see that Gibbs has almost systematically higher values than Xiaopeng-Li's method. So there is like a trend here. Again, due to the few sample size, we didn't made any R-square analysis or whatever, but there is a tendency. And if you go to the root mean square, normalized root mean square error, you can see that most of the calibration results are within a bound of 0.1. So we reject all what is out of 0.2 there. So only this part of the figure is used. But you can see that there is no tendency. We cannot say that one of the two methods is better than the other. So if we compute mean and standard deviation, then we have these results on this small sample again. In the literature, many authors report human-driven reaction times. My value I had in mind was 1.2, but recently reading Lee's and Chen paper, I realized that for them, the normal human-driven car response time is 1.5, which is for me a big large, but okay. And you can see that the mean values of all these 64 trajectories is significantly larger than 1.2, and for Gibbs even from 1.5. And you can see also that different methods produce very different results. So then can we try to find a reason why? I think, and this is because there is behind the question of the response time definition. Makridis methods focus on the response time to a stimulus, and this is an external method based on observation, and this is very specific compared to the three other methods which are for Newell. There is a parameter in the car following equation, but this is not the results of a calibration procedure, but this is at least a parameter in the linear relationship. And for Gibbs and Xiaopeng-Li, we use clearly calibration method. So this is a difference between the two, and we have also to go into the details of the car following rules, because the response time there have different definitions. But sometimes they are used, one word is used for the other concept. For example, in many car following models, tau is named the response time to a stimulus. But in reality, if you go to the very big details of the car following equation, you can see that this claim, this is the response time, doesn't survive to real analyze, because the formulation of the equation and the numerical resolution of the equation modifies the meaning of the parameter. This is a classical thing in calibration of any model, but this is something maybe we have too much forgotten in our community. There is also, this is not the purpose of this talk, but please keep in mind that there is also the question of the numerical resolution time step, which is sometimes and in many occasions confused with the parameter of the car following equation. And this is also a problem, especially if you want to have response time adapted to each vehicles, or if you want to have distributed values of response time. So if I go now to the conclusions, and again we confirm that the ACC response time are larger than the one previously reported for human-driven vehicles. So this is not very original, but we have that for the same data set with various methods. The difference in the results depends on the method, and there are also many other dependencies that we may scrutinize in the next future. And the difference, depending on the method, comes from the difference of the definition in response time. And as soon as we get more data, we will proceed to more computation and then have better conclusions for a future paper. So thank you for your attention. This is my reference list. Thanks to all contributors in there and the others. That's it. Thank you. Thank you for coming.
Christine, for your first observation, like the reaction time is larger than human drivers. So I recall using Tina's method, what we saw was that for the small headway, the reaction time was actually smaller than human driver. But then if you have large headway, then it is larger than human driver.
Yes.
Yeah. Yes. So I remember we had the same observation when we look into Danworks data. So it depends, it varies with the headway. Usually at the smallest headway, it's smaller than human driver, but at the largest headway is larger than human driver.
Well, actually, for human drivers, there might also be a headway influence on the reaction time. If someone drives close to his predecessor, he might respond quickly. But there might not be just one value, but also a range.
Yeah.
Does that make sense?
This is a Xiaopin, and I really appreciate your work, and this is a very interesting talk. Yeah, and I just want to follow up with D'Andrea's comments. So it seems like all these ACC vehicles have some kind of different settings, customized settings of the headways. Yeah, the papers we published discussed them a little bit. It looks like that will affect the range. We also had another piece of work on its impact on fundamental diagram and having similar conjectures going to be if everyone sets up the smallest headway, our traffic will be a bit less congested. If they all set on the longer headways, traffic is going to be more congested. That's one thing. Another thing is actually, that really the response time has like human reaction and mechanical reaction and this kind of thing. So lots of nonlinearity. Even if it's the same vehicle, if you have different lead trajectories, you may get different response time from just the linear or Gibbs model. So I think really if the trajectory is smoother, so the reaction time tends to be longer, I guess. This trajectory has lots of acceleration, decelerations, maybe see shorter responses. But I mean, these are just my observations and conjectures. I think that's a promising research direction and lots of interesting thing to understand of ACCs, and also different manufacturers have different settings. Yeah.
I wonder, this is Ping Yi. I wonder if the results had things to do with the kind of detection. Okay, depending on different models you use, what kind of detection technologies are used in different vehicles. And the statement made before that when the spacing.
Excuse me. Do you mean measurement device?
Yeah.
Or the sensors inside the
sensors and how you measure also.
Okay.
I mean that if you have a precise data to say when the system received that, but then from receiving to the reaction, I mean even in mechanical system, it will take some time. So if we can different phases, if we want to break that into different phases, can be separated, then maybe we'll have better understanding. But I'm saying is here, a statement, I think it may provide indirect, I want to say proof or evidence that to lead people think that way. That is, the spacing or headway, if it's closer, then the reaction time is faster than a human driver, than a longer headway. Okay, if a longer headway, I guess maybe it's more difficult for the sensor, to detect and react, and react the same, but to especially detection part. I'm just saying maybe indirectly that that has some shows something there if we can get into the different data stages. Just a single point comment.
Mm-hmm. Thank you very much. May I ask to Victor to ask his question again, because I didn't get it.
It seems that Victor is gone.
Ah, okay. Thank you.
This is Ben Koifman again. There's, this is all fascinating material, and it's kind of like the automakers are effectively designing our fundamental diagram as a result of their adaptive cruise control. But at least in the first order approximation, I'm going to guess that the automakers are not thinking about throughput for a given lane. And I kind of wonder, from a traffic flow perspective, the certainly longer headways are going to bring down your capacity, but that's still, even if you reduce capacity, just harking back to what Xiaoping said, it might still be better to have lower throughput, but fairly constant speed of 30 miles an hour or 40 miles an hour or whatever that maps to in kilometers per hour, and having that constant if the adaptive cruise control can dampen the disturbances, and that's going to be especially true in mixed traffic where you've got instrumented vehicles and human-driven vehicles without the adaptive cruise control. So that's an interesting direction, I would think, that can branch off of this. And I think this is an area that you've been interested in for years, which is how can the traffic flow theory community actually influence the automakers and make traffic do what we want.
It leads me to this figure, because you say that ACC may dampen human driver overreaction, but what we see there, and this is for me a very important research direction, the question of the stability of the platoon is really, really important.
Oh no, I mean in the ideal case we want it to dampen.
Ah, okay.
Yeah. What the current systems do right now, I think, is going to be all over the map, because I would imagine a current system you could make it, just by adjusting the target headway, you could make it dampen or amplify. And the existing systems aren't perfect. It's always fun when the adaptive cruise control picks out fixed object and goes, whoa, I need to hit the brakes real hard. Or alternatively, when it misses an actual vehicle in front of you. So I've had both of those happen to me, just driving cross country.
Okay. Any further question?
Maybe not a question. Christine, maybe let me share with you something that we saw recently, because it's related to this one. Yeah. So I analyzed some kind of data shared by Waymo, the self-driving car, and then because they also have the data from like human-driven car in that sensing, using the same method, just extract the stationary points, and then got this relationship between the speed, horizontal, and then spacing in the vertical. The green dots here are for Waymo, and the gray ones are for human driver. So because of the data limitation, it's mostly in arterial traffic, so the speed usually does not go over by 20 meters per second. But what you can see is that the regression outcomes are quite different. And so if we use the same method, right, to extract the tau, so for Waymo, it's about 1.3 seconds. For human, surprisingly low, it's like 0.73. I don't know why. Maybe some. Yeah. And then what does this mean? It means that the Waymo capacity, so if you assume that free-fall speed is like 20 meters per second, then Waymo is only like 67% of human traffic. And then if we increase this to be 30, then it's about 64. So that means a huge reduction in the capacity.
Thank you for sharing.
Yeah, so this is, I don't know how it will look when we calibrate it using your methods, but it will be interesting to see. I can share the data with you if you like.
Okay, good. Very good.
Okay, very good. Any other question from the audience here? Okay, if not, let's thank Christine with a big applause. Thank you, Christine. It's a very interesting talk. So